So today I want to do some examples with the contraction mapping principle. And this has to do with integral equations. So a type of integral equation that comes up quite a lot is something called a Fredholm type. Named after the person who first considered these. And typically it looks like this. Y of x is some parameter mu times the integral a to b of some function a of xy times dt plus some function of x.
Are those all functions of t?
No, not this one. So we're looking for a solution of such an integral equation. So we look for a solution y of x on the interval a to b. And here, v of x is some fixed function. So the question is, when can you solve such a thing? So here's a particular example. Suppose we had the equation y of x is equal to the integral from 0 to 1 e to the xt y of t dt divided by 3 plus sin x. So this would be a particular example of such a thing. I'm off to a bad start here. This is just t. Okay. So the way we can do this is we can regard it as a fixed point problem. So we can define the right-hand side as a function. And what it does is it takes continuous functions on 0, 1 and gives you back continuous functions on 0, 1. So t phi at x is the integral 0 to 1 e to the xt phi of t dt divided by 3 like to see that that is a contraction. And so if we figure out what t phi minus psi is, so functions phi and psi in the continuous functions on 0, 1, we have the following, that t phi at x minus t psi of x, just put phi and psi into the formula, take the difference. Now the sin x terms will cancel, and we'll be left with the integral 0 to 1 e to the xt over 3 5t minus psi of t integrated dt. And therefore, if we want to estimate the difference, it's the absolute value of that integral, which is less than or equal to what we get when we bring the absolute value inside. So this is less than or equal to the integral 0 to 1. Now e to the xt over 3 is positive, so we don't have to do anything about that. And then we will have absolute value p of t minus psi of t dt. And that last absolute value is bounded by the infinity norm of the difference. So this is at most the integral 0 to 1 e to the xt over 3 times the infinity norm of phi minus psi integrated dt. And now we can estimate how large that is when x and t are between 0 and 1. The product xt is, and so we have here at most e. So this is less than or equal to the integral 0 to 1 of e over 3 it's now just the integral of a constant. And so this comes out to be, at most, e over 3 times the infinity norm. Since e is 2.7 something something something, that ratio is less than 1. Since e over 3 is less than 1, we have a contraction and as a consequence, t has a fixed point in the interval, or rather in the continuous functions on the interval 0, 1. So there is a continuous solution to this equation. And therefore, the equation has a unique solution. Okay, if it turns out not to be a contraction, which is possible, then there are a couple of things that you can do. One of them is to look at the square, squared. Because we had that theorem that said if a power of t has a fixed point, then that is also a fixed point for t, and hence a solution to the equation. So what one can do is compute t squared or t cubed or whatever, and then that could eventually be a contraction. In fact, we'll see an example later today about that. Now, how could we get t squared out of this? So let's have a look at this equation. Y of x is equal to the integral from a to b k of xt y of t dt plus v of t.
V of x.
V of x. Now, what we usually do is we write t for the right-hand side. But what we can do here is let us write t of y at x. Let's use a different symbol, and let's write s of a function phi evaluated at x is just the integral part. And so the relationship is that t at phi is s applied to phi plus the extra function on the end. Now, if we replace phi by t of phi, then what we get is t squared of phi at x is s applied to t because of its integral form, when you apply it to a sum of two things, it's the sum of the individual s's applied because of the integral here. And so this is s squared applied to phi of x plus s of v of x plus v of x. So it kind of has the same form once we figure out what s squared is, because this is just some fixed constant function at the end here. So the question is, what is s squared? If I apply s twice, what do I get? So s squared phi at x is s applied to s phi at x so according to the formula, it's the integral from a to b k of xt times s phi at t integrated dt. And now we just have to put in the formula for s phi. Now we need a different letter. X has become t, and so we'll use s for the u for the integration. So a to b k of xt, and then it will be integral a to b k of tu times phi of u du integrated dt. So I'm just making a substitution there for s. So I make this into a double integral, a to b, k of xt, k of tu, phi of u du dt. But now if I change the order of integration and do it dt du instead, which is fine because I'm on a square, a to b and a to b, then if I do the t integration first, I'll get integral a to b k of xt k of tu dt times phi of u du. Now if you look at this, the integral inside here, when I integrate with respect to t, I end up with a function of x and u. So this has the form a to b, let's call it k sub 1, this new function is equal to the integral a to b k of xt k of tu dt. And therefore, t squared looks like this. T squared b at x is the integral a to b of this new kernel function, k1 of xu phi of u du, but the bit on the end is different. So I get this. So what I've done is I've changed the kernel function from k to k1, and I have changed the final function from v to sv plus v. But this is the integral equation of the same type as before. Now, what we found before was when we took the infinity norm of the kernel, which was e to the xy over 3, that was less than 1, and that determined whether it was a contraction or not. So here, this will be a contraction if the infinity norm of k1 is less than 1. So if the first one isn't, then maybe this one is. And you can do it again, and maybe t cubed is. So a particular example is an equation of what is called Volterra type. So here it would be y of x is the integral a to x, and with some parameter mu in here, of a function k of xt, y of t dt, plus some fixed function v on the end.
Those two x's are supposed to be there, right?
Right. Okay, so actually it doesn't quite look like what we had before because we were integrating from a to b. change the kernel, k of xt, this is a Fredholm type. And the way to do that is, for a fixed value of x, we're only integrating t from a to x. So in the square a to b, this is x, and this is t. For a fixed value of x, the t integration is only taking place from a up to x. So if I draw in the diagonal there, I'm only integrating that far. That would be the same as integrating a to b if the kernel function was 0 up here. So we can define a new kernel to be this. It can be k of xt provided that t is below x and 0 when t is bigger than x. So what that does, it simply takes the function that's defined over this square and says above the diagonal you make it 0. And then the integral from 0 to x, k of xt y of t dt, is equal to the integral a to b k1 of xt y of t dt. So although the one I wrote down didn't look like one of these integral equations, by manipulating the kernel, you can make it one.
How do you know what B is going to be? It's just the what you're given.
Oh, yes. So you're looking for a solution of continuous functions from a to b. B can be anything. Now, the nice thing about these ones is that even if k itself is not bounded by 1, powers of these will be. So for Volterra equations, t to the n see why that is. For any two functions, p and psi, t phi minus t psi at x will be mu times the integral from a to x. We'll go, now that we've seen it's one of these integral equations we've been talking about, we'll revert to the original formulation, a to x, and we will have k of xt, phi of t minus psi of t, dt. So let's write C to be the infinity norm of k of xt. Then the absolute value of t phi minus t psi at x is at most the absolute value of mu. I'll estimate the k of xt by the constant c. So it'll be the integral from a to x c, and here I'll take the infinity norm of phi minus psi integrated dt. And what I find is that this is less than or equal to the absolute value of mu times c times the infinity norm of phi minus psi. And then when I integrate, I get x minus a. No reason to believe that's a contraction, because mu and c can be anything. However, if we do it again, now in place of phi minus psi, I'll have t phi minus t psi. And so I can put in the estimate for that. So it will be absolute value of mu times c times the infinity norm of phi minus psi multiplied by x minus a, or t minus a in this case. dt. So I have a bunch of constants there, and I'm just integrating t minus a dt from a to x. And so this is at most absolute value of mu squared times c squared times the infinity norm of phi minus psi times x minus a squared over 2. time and you'll see a pattern emerging. So again, let us replace phi and psi by t squared phi t squared psi. And we find that the absolute value of t cubed phi minus t cubed psi at x is going to be at most absolute value of mu times c, the integral from a to x, and then inside we'll have the infinity norm of phi minus psi times t minus a squared over 2 integrated dt. And I also have a mu squared c squared coming from the previous estimate. And this time, when I integrate, I get that it's less than or equal to the absolute value of mu cubed, c cubed, and now I integrate t minus a squared over 2, which gives me t minus a, x minus a cubed, divided by 3. I already have a 2, so that is a 3 factorial. And I also have the infinity norm of phi minus psi. Well, if you just keep doing this, in general, what you find is that t to the n phi minus t to the n psi, evaluated at x in absolute value, is at most absolute value mu to the n times c to the n divided by n factorial times x minus a to the nth power times the infinity norm of phi minus psi. So you just keep plugging back into the formula for t, and you get this estimate. So at this point, if you maximize over x, the maximum occurs when x is equal to b. So therefore, the infinity norm of t to the n phi minus t to the n psi is no larger than the absolute value of mu to the n, c to the n, times b minus a to the n, divided by n factorial times the norm of phi minus psi. So in order for this to be a contraction, all we need is that for n large enough, this number should be less than 1. But the point is that this number, let's call it an, an is the nth term in the Taylor series. E to the x is 1 plus x to the n over n factorial plus and so on. When I plug in x is equal to value of mu times c times e minus a. Since the Taylor series for e to the x converges, the terms go to 0. So this series converges. And consequently, an goes to 0 as n goes to 1. So no matter what value of mu and c we started out with, if we do this a sufficient number of times, we will eventually get a contraction. And so, therefore, t to the n is a contraction for n large enough, and so the original t has a fixed point. So the Volterra equations always have solutions. And you can see here, for a fixed kernel k, well, you have the bound c. If you increase mu, then you'll have to take larger and larger powers to get this number down below 1. And so it may well be that you have to take an enormous number of powers to arrive at contraction. You will eventually get one. Okay, so that's time today. I plan to have one last homework sheet, so I'll probably get that out tomorrow for you. The other thing is, 447 is going to be taught by Dr. Douglas, and so he's going to come along on Friday for the last 10 minutes and